Good morning. This is the second video recorded lesson for learning outcome 10. Okay, in the first lesson I mainly revised the year 9 material. We went over mass number, relative atomic mass, isotopes, and we also started introducing for the first time the idea of the mole as a quantity, as a huge number in chemistry. If you remember, we said that the Avogadro's number, which represents the mole, okay, if you like, is equal to 6.02 times 10 to the 23. It's just a number. We also went further and we said that the Avogadro's constant is 6.02 times 10 to the 23 per mole. It could be atoms per mole, it could be molecules per mole, it could be ions per mole, whatever. Okay? Now, in this particular lesson, we are going to apply what we learned in lesson 1, so that we can now calculate relative molecular mass, relative formula mass. These are required for your MedSec assessment criteria 10.2a. Do check out your MedSec syllabus to see for yourself. Also, we shall once again be focusing on the mole, and we shall start doing first calculations using the mole. These are leading you, okay, to complete MedSec assessment criteria 10.3d, but it's not all of 10.3d. It's only a small part of 10.3d. 10.3d will be fully covered by means of other subsequent lessons. Let's now go on to the next slide. Throughout this lesson, you will learn these 4 principal learning outcomes. The first one is that you will know for sure that a mole is all about an amount of any substance. When we say a mole, we are referring mainly to the Avogadro number of particles. So if I say I have a mole of magnesium atoms, it means I have 6.02 times 10 to the 23 atoms of magnesium. It's a collective quantity. You will also learn about calculating relative molecular mass and relative formula mass. We shall distinguish between the two terms by means of adding the relative atomic masses of the individual elements together. Then, something that I've already introduced in the first presentation in lesson 1. You should definitely know by the end of this presentation that if I have, for example, the mass of 1 mole of iron, how do I find the mass of 1 mole of iron? If you remember, you have to take your relative atomic mass, which in the case of iron is 56, you express it in grams, 56 grams, that's the mass of 1 mole of iron. Finally, you will be able to convert moles of substances, so for example a mole of magnesium, into the mass of a substance. This is related to the third learning outcome. Okay, so if I have a mole of magnesium, you will know that it will weigh 24 grams, and vice versa. If I have 24 grams of magnesium, it is a mole of magnesium. If I have 48 grams of magnesium, it has to be 2 moles of magnesium atoms. Let's now go on to the next slide. Let us get back to the mole. We have to be very, very clear about the idea of the mole. Okay? The mole in chemistry is a quantity. It's a very, very large number. It is based on the Avogadro number, and the Avogadro number is 6.02 multiplied by 10 to the 23. So we have 23 zeros. Now it could be, you could have a mole of anything, okay? You could have a mole of atoms, a mole of molecules, a mole of ions. I remind you that ions are charged chemical species. They can either be positively or negatively charged. So if I say that, for example, I have a mole of sodium ions, I would have 6.02 times 10 to the 23 of Na+. Okay? Now, whatever the element is, it makes no difference. If I say that I have a mole of atoms, it could be a mole of carbon atoms. A mole of carbon atoms is 6.02 times 10 to the 23 carbon atoms. If I have a mole of iron atoms, it's also 6.02 times 10 to the 23 atoms. I remind you every time that 6.02 times 10 to the 23 is called the Avogadro's number. Now, the number is really used in chemistry because it's so useful. If you could count this many carbon atoms, okay, if I had to count exactly 6.02 times 10 to the 23 carbon atoms, they would add up to a mass of exactly 12 grams. Okay, so in other words, the mass of 1 mole of carbon atoms equals 12 grams because 6.02 times 10 to the 23 carbon atoms, which is 1 mole, is equal to 12 grams of carbon. Also, at the same time, it gives you an idea of just how small and how tiny and how light atoms are. You have to add such a huge number of carbon atoms all together to give you just 12 grams. Okay? But by means of using such a large number, I can then use a simple top and balance in the laboratory to weigh out carbon in exact amounts. So if I weigh out 12 grams of carbon, I know exactly how many atoms of carbon I have in there, and I can do what are called quantitative or exact numerical calculations based on my weighing. Now, we know from the first lesson and also from your year 9 that the RAM, so the RAM is the relative atomic mass of carbon, is equal to 12. So I'll write it over here. The RAM of carbon is 12. Okay? And the RAM of hydrogen is of course 1. Okay? 1 atom of hydrogen weighs 12 times less than 1 atom of carbon. So if 1 mole of carbon, remember what I said in the first lesson, if you want to calculate the mass of 1 mole of carbon, convert the RAM, express it into grams. 1 mole of carbon converted in, so if I have the RAM of carbon, is 12. If I had to write it as 12 grams, that is how much 1 mole of carbon weighs. Now, if I had to have, of course, the RAM of hydrogen is 1, so 1 mole of hydrogen weighs 1 gram, which is exactly what you would expect. You would expect a mole of carbon atoms to weigh 12 times as much as a mole of hydrogen, because each atom of carbon weighs 12 times as much as an atom of hydrogen. So if 1 atom of carbon weighs 12 times as much as 1 atom of hydrogen, then if I have 1 mole of carbon, by a logical extension, it has to weigh 12 times as much as 1 mole of hydrogen. So 12 grams for carbon, 1 gram for hydrogen. Let's now move on to our next slide. So in the slide, we shall for the first time use relative atomic masses to calculate both relative molecular masses and relative formula masses. Now let's distinguish between the two as we go along. By example is best. Well, molecules that you are familiar with do include carbon dioxide and water, and since they are molecules, they are simple covalent molecules, they are made up of atoms which are linked together with covalent bonds. Okay? We say that we have a molecule. Okay? So if I want to compare the mass of a molecule compared to 1/12 of carbon 12, I say that I have a relative molecular mass. Okay? Let's look at example 1. An abbreviation for RMM, by the way, is M subscript R. RMM, relative molecular mass, M subscript R, all mean the same thing. So in an example 1, we are being asked to find the relative molecular mass of carbon monoxide. So it is a relative molecular mass. Why? Because carbon monoxide occurs as simple covalent molecules. So it is correct to use the term RMM, okay, because we are referring to molecules. Now, remember that we compare always the mass of the molecule with 1/12 of carbon 12. 1/12 of carbon 12 is exactly 1. If it confuses you, you can also think of an atom of hydrogen, which has an RAM equal to 1. So look up, look up the RAM of carbon. The RAM of carbon is 12, okay? Look it up in the periodic table. It's the larger number at the top left-hand corner. Okay, you have only one atom of carbon in carbon monoxide, so all you do is put down 12 once. You don't multiply it by anything. Likewise, oxygen. Oxygen has a relative atomic mass of 16. You have only one atom of oxygen, so you put down 16 once. Notice, I will refer to the calculation that you have at the bottom of the screen. You have your 12 from carbon, your 16 contribution from oxygen. All you have to do is add up the two, and this is the relative molecular mass of carbon monoxide. Now, if we had to get to the second example where we have sodium oxide, well, as you should recall from your valency studies, okay, from your previous valency studies, sodium is a group 1 element, so it has one electron in the outermost shell, and it will prefer to lose one electron, therefore it has a valency of 1. Oxygen is found in group 6. It has 6 electrons in the outer shell. It prefers to gain 2 electrons, so it has a valency of 2. In order to find the formula, the chemical formula, as I always do with my students, we cross over those valencies, okay, so that the resulting formula is written as Na subscript 2O. So that's sodium oxide. Notice that sodium oxide contains 2 sodium atoms for every oxygen atom. And we have to take that into account when calculating the relative formula mass. Notice it's not relative molecular. Why is this? Because sodium oxide is an ionic compound. And an ionic compound, in this case, it consists of 2 Na plus ions. Okay, so there are 2 of Na plus, and I will put them down here. Okay, imagine there is 2 of Na plus for every one of O2 minus. Notice that the charges are balanced and neutral. You have 2 positives and 2 negatives, add up to 0. Na2O is overall electrically neutral, so it makes sense. But since we have a giant ionic compound, we cannot talk of relative molecular mass. It would defeat the purpose of saying it's an ionic compound. So we have to use a different term. We say it's a relative formula mass. No one can tell us, listen, this is not a formula. What is it? It's a chemical formula. So it's a relative formula mass. But since we are referring to the formula, we have to take into account all of the atoms. So when calculating the relative formula mass of sodium oxide, remember relative, comparing it to 1/12 of carbon 12. 1/12 of carbon 12 is exactly 1. So I have sodium. How many sodiums do I have? I've got 2. So in that case, I have 23 by 2. Okay, I remind you that 23 is the RAM of a single sodium atom when compared to 1/12 of carbon 12, or when compared to an atom of hydrogen. But since I have 2 sodiums, therefore I must multiply by 2, and that of course will be 46. Okay? Now, for every 2 sodiums there is just 1 oxygen. Oxygen has an RAM of 16, there you go. And therefore, to calculate the RFM, the relative formula mass of sodium oxide, I add together the 46 and the 16, and so my result is of course 62. In other words, okay, the relative formula mass of sodium oxide is 62, and it shows us that sodium oxide will weigh 62 times as much as 1/12 of carbon-12, or as much as an atom of hydrogen. Let's now go on to the next slide. Now over here we have another 2 examples. I've left a space over here. I will indicate where on purpose so that I can draw in a formula, rather a structure of a formula that will interest you. We've got sulfuric acid. Notice that we are referring to relative molecular mass. M subscriptar is an abbreviation for relative molecular mass. Now, why are we talking about a relative molecular mass? Why are we talking of sulfuric acid as being a molecule? Well, because that's exactly what it is. Sulfuric acid, now you don't really have to know this, but I am proving that it should be called a molecule, okay? And so we use the term relative molecular mass. Notice that sulfuric acid is first of all made up of non-metallic elements. All of them are non-metallic. And as you might expect, therefore, the bonding will be fully covalent. Since it's fully covalent and it forms simple molecules, we therefore refer to RMM. You did all about acids, bases, and alkalis. What makes sulfuric acid a very strong acid are these 2 hydrogens that are fully dissociated, fully separated from the rest of the molecule when sulfuric acid is added to water. Okay, it releases a tremendous amount of energy. That's why you have to be really, really careful when adding the acid to water. The correct way for safety, just to remind you in the lab, is to add a very small amount of acid to a large amount of water, in which case the acid is immediately diluted by the large volume of water and you disperse the heat generated. Now, look at the structure. Notice that there is 1 sulfur, okay? There are 4 oxygens, and there are 2 hydrogens. So I have to take all of that into account when calculating the relative molecular mass. So what I do is, I start with hydrogen. Hydrogen has an RAM of 1, but there are 2 hydrogen atoms, so I have to multiply by 2. Likewise for oxygen. Notice, in the case of oxygen, we've got 4 oxygen atoms. So the relative atomic mass for oxygen has to be multiplied by 4. In the case of sulfur, there is only 1 sulfur, and that's where it is. Okay, it's got a relative atomic mass equal to 32. So the relative molecular mass of sulfuric acid is found by adding together the RAMs according to the chemical formula. The chemical formula is telling us, listen, there are 2 atoms of hydrogen, 1 atom of sulfur, 4 atoms of oxygen. Add them together in that ratio using the RAMs, and you have the relative molecular mass. If we were to refer to the final example, copper 2 sulfate. Now, just a very brief revision of valency. Once again, when you see the Roman numeral 2, it's referring to the valency of copper. You have no problem about that. Okay, be sure of that. So copper valency 2 is expressed in that way. Sulfate, you should know, has a group valency equal to 2. Okay, I can even put a bracket around the sulfate if you like. Okay, the 2 goes down there. The 2 goes down there, so we have a crossover. And since they are equivalent, we cross them out. And the final formula is, of course, written as CuSO4, which is copper 2 sulfate. Okay? So, once again, in order to find, now it's an ionic compound. It's an ionic compound consisting of Cu2 plus ions, okay, and SO4 2 minus ions. If you are ever in doubt about whether a substance is ionic or covalent, look at the atoms. If there is a metal atom at the front and the remainder is non-metallic, the chances are it's going to be an ionic compound. At O level, certainly so. If it's an ionic compound, you don't refer to it as relative molecular mass, but you talk of relative formula mass. But the principle is the same. You have CuSO4, you've got one copper ion, and then making up the sulfate anion, you have a sulfur and 4 oxygens, okay? So one copper has a relative atomic mass of 63.5. Sometimes it's given as 64 in your periodic table, okay? We have one sulfur with 32, and this time we again have 4 oxygens, so we have to do 16 by 4. Add them all together as we did for sulfuric acid. The result is 159.5. That's the RFM. How many times heavier, okay, copper 2 sulfate is than either an atom of hydrogen or 1/12 of carbon 12, okay? If you had to look at the picture on top of me, you've got also water, okay? Now, this is to reinforce the idea of why it is so important to know about relative molecular mass, relative formula mass, because then we can use it for calculations in chemistry. Let's look at a single water molecule. A single water molecule consists of two atoms of hydrogen. Okay, so I've got 2 atoms of hydrogen, and of course I've got an oxygen atom. Now the oxygen atom has a relative atomic mass of 16, and the hydrogen has a relative atomic mass of 1, but I've got 2 hydrogens, so I have to put it down twice. All in all, the relative molecular mass of a molecule of water will add up to be 18. Now remember what we also said in our first lesson. If I had to have 1 mole of water molecules, 1 mole of water molecules would be equal to 6.02 times 10 to the 23 water molecules. A huge amount of water, isn't it? Okay, you might imagine, but water molecules are so tiny that 1 mole of water molecules would simply weigh as much as the relative molecular mass, which is 18. But remember what we said, you express it in grams. If I had to convert it into grams, that is the mass of 1 mole of water molecules. So 1 mole of water molecules, or 6.02 times 10 to the 23 water molecules, are found in just 18 grams of water. And since 1 gram of water is equal to 1 mil, therefore I have a mole of water molecules in 18 mils of water. So now you can easily calculate how many moles of water molecules you have in a 2-liter water bottle. Okay, so next time you fill up your water bottle at your school, okay, and you fill it up with 1 liter or 2 liters, you know exactly how many water molecules you have actually added to your water bottle. I am sure that that students who don't study chemistry would be very, very fascinated by what you can actually calculate with a very basic knowledge of chemistry. Let's now go on to the next slide. So over here, as you're getting used to the way I do things, I include many, many examples of the same thing, probably drive you mad sometimes, because I mean, but anyway, it's a way of making sure that students do understand. I've included a table and in a different format of how we can go about calculating relative molecular mass and relative formula mass. Okay, I've taken 3 examples. Water, which as we know consists of simple molecules, H2O, therefore I have to call it RMM. But then take note, when I am talking about NaOH. Since NaOH is an ionic compound consisting of Na plus and OH minus, okay, therefore I have to refer to it not as relative molecular mass but rather as relative formula mass. Likewise for magnesium hydroxide. Remember what I said in the previous slide. If there is a metal atom at the front, the chances are it is ionic. Okay, so in this case magnesium hydroxide, I've got Mg2 plus and 2OH minus ions. Okay, so once again I have to refer to it as relative formula mass. Now let the formula lead you to the calculation. What I mean is this. When you have a formula of H2O, in order to calculate the RMM from the RFM, you have to take in the ratio of the atoms. So since you have two hydrogen atoms, note over there, so the RAM of hydrogen must appear twice. You have a single oxygen atom, 16, the RMM is the simple addition. If I had to look at sodium hydroxide, all atoms appear once, so that's sodium, that's oxygen, that's hydrogen. Together they give us a relative formula mass of 40. If I had to look at magnesium hydroxide, don't let it confuse you. The 2 outside the brackets means that both the oxygen and the hydrogen have to be doubled. So magnesium is done once, it's 24. We have 2 oxygens and 2 hydrogens, so all in all, it works out to be a relative formula mass of 58. In order not to confuse you, I've clarified whether it's relative formula mass or relative molecular mass right next to the chemical substance. Let's now go on to the next slide. So the relative molecular mass, as you should definitely know at this stage, may be defined, okay, so I'm referring to right over here, to how much heavier a molecule covalent compound. That's why it is a molecule covalent compound. In this slide, I've referred to specifically carbon dioxide, okay, which is CO2. How much heavier it is, either when compared to a single atom of hydrogen, which has a relative atomic mass of 1, or how much heavier it is than 1/12 of carbon-12. Since carbon-12 is 12, 1/12 of 12 is of course exactly 1. Okay, so if I had to talk about the relative molecular mass of carbon dioxide, now first of all it's RMM not RFM, because carbon dioxide exists as simple molecules, covalent molecules. We know, okay, even people who know no chemistry know that carbon dioxide is CO2. So the ratio is 1 atom of carbon is to 2 atoms of oxygen. So in order to find the relative molecular mass of carbon dioxide, all I have to do is add the RAMs. Carbon is 12, okay, and oxygen is 16 multiplied by 2, because I've got 2 oxygen atoms, okay, so all in all, that will work out to be exactly 44, okay? So that's all you have to do. You can also check out the calculation at the bottom over here, okay, but I prefer to explain it in this manner. Perhaps it's clearer, okay, which is why I am doing this in the first place. If I had to consider this second diagram over here, okay, notice, consider having a molecule of hydrogen. One molecule of hydrogen has an RMM of 2. First of all, we talk of a molecule of hydrogen. Very quick revision of Form 3 work. Remember that a hydrogen atom contains a single electron. A second hydrogen atom will bring another electron. They will connect together using a single covalent bond. So the whole thing is a hydrogen molecule, H2 molecule. It has an RMM of 2, meaning it weighs twice as much as a single hydrogen atom. So if I had to imagine I had an atomic balance, If on the one side I had a single hydrogen molecule, it would be perfectly level with two hydrogen atoms, because a hydrogen molecule has an RMM of 2, and each hydrogen atom has an RAM equal to 1. Okay? Let's now move on to our next slide. Over here we have a first experience, or a further experience using calculations with moles and masses of substances. Okay, we're getting used to this idea of converting moles into masses of substances. So I remind you once more, okay, that if we had to consider a mole of a molecular compound, okay, a molecular compound such as water, okay, the mass of 1 mole is equal to its relative formula mass, but expressed in grams. So a mole of water, 6.02 times 10 to the 23 molecules of water, has a mass of 18 grams. Remember that that is equal to 6.02 multiplied by 10 to the 23 molecules of water. Okay, as we said also in the previous slide, we also went through the idea that a mole of carbon dioxide, since it has a relative molecular mass of 44, convert that 44 into grams, so a mole of carbon dioxide has a mass of 44 grams. What works for relative molecular mass works just as fine in terms of relative formula mass. So if we had to consider ionic compounds rather than simple molecules, if we have sodium chloride, okay, notice the ratio. We have 1 sodium ion, Na+, okay, and 1 chloride anion, Cl-. The sodium ion has a relative atomic mass of 23, the chloride a relative atomic mass of 35.5. Remember what we said about relative atomic mass from isotopes when we did the chlorine example in the first lesson. Okay, so if I had to add together the RAMs of sodium and chlorine, I would end up with 58.5 as you have in your printed text. Okay, so 58.5 grams is the mass of 1 mole of salt. So if you had to weigh out 1 mole of table salt, it would be done by weighing 58.5 grams. You could also, for fun, okay, the WHO allowance for keeping your blood pressure low is that you should take no more than 6 grams of salt as salt, NaCl, per day. If you are calculating it as a sodium allowance, it works out to be around 2.5 grams of salt as sodium. But if you have to take the whole thing, 6 grams of NaCl. So you could decide, you could find out how much in terms of moles of NaCl is equal to the WHO limit. All you have to do is a simple proportion. 1 mole of sodium chloride is equal to 58.5 grams. How many moles of sodium chloride is equal to 6 grams? 6 on 58.5, it's approximately 1/10 of a mole of sodium chloride. That's what you must not exceed in order to keep your blood pressure safe. If we go on to look at oxygen gas, oxygen is of course diatomic, meaning that there are 2 atoms per molecule. Okay, now since each atom has a relative atomic mass equal to 16, therefore oxygen must be 16 by 2, that's 32. That's the relative molecular mass of a single oxygen molecule. If I want to convert that into grams, what I end up having is the mass of 1 mole of oxygen molecules. 1 mole of O2, okay, weighs 32 grams, and 1 mole of O2 is in turn equal to 6.02 by 10 to the 23 molecules of oxygen. Okay? So if I have a mole of oxygen atoms, it will weigh 16 grams. It is a mole of oxygen molecules that weighs 32 grams. Watch out for such tricks in examinations, okay? Because students frequently get confused. From my own experience, they tend to confuse molecules with atoms, okay? So watch out for what the examiner is asking. If you have to look at the picture over here, right at the top, it gives you an example of just how useful moles are, okay? A mole of magnesium would, for example, weigh 24.3 grams. Now, why are there decimals? Well, because these are very exact amounts. For the periodic table that you have at O level, we have truncated, we have simplified the decimal places, and we have expressed magnesium as being 24. If you look at, for example, copper, many times, copper is found as 64 rather than 63.5. Okay? We don't even put a decimal after the 12 in case of carbon. We just write it as 12, not 12.0. Sulfur also is 32. Well, basically, the picture shows us the mass of 1 mole of substance. So, since, for example, sulfur has a relative atomic mass of 32, we put in the grams, and as we said, the relative atomic mass expressed in grams is the mass of 1 mole of that substance. So 1 mole of sulfur atoms will weigh 32.1 grams, 32 grams. Likewise, for example, lead has a very high relative atomic mass. It's a very heavy metal. It actually is classified as a heavy metal. Okay, it has a relative atomic mass of 207. If I want to know the mass of 1 mole of lead atoms, all I have to do is put the G after the 207. 1 mole of lead is 207 grams. Let's now move on to our next slide. So once again, some further examples of relative molecular mass and relative formula mass and the relationship with the mole, okay? So if I had to look at the first bullet over there, I've got 1 mole of carbon monoxide. If I'm asked how much will this weigh, all you have to do is this. Find out the RMM. The RMM is found by simply adding together the relative atomic masses, okay? So to help you out with this, the relative atomic mass of carbon is 12 and the relative atomic mass of oxygen is 16. Notice 12 is just once, 16 is just once, because in the formula carbon monoxide there is just 1 atom of carbon, 1 atom of oxygen. So the relative molecular mass is 28. Then all I have to do is to express that in grams, as I've done there, and there we have the mass of 1 mole of carbon monoxide molecules. 1 mole of sodium oxide, okay, we've already calculated on a previous slide. So I'd like you to go back to that slide, also revise, okay, how we got to 1 mole of sulfuric acid and 1 mole of copper 2 sulfate. Basically, this slide is a revision slide. Once again, when you look at the diagram over here, the picture, it's really emphasizing just how small and tiny atoms are. A mole, which is a huge number, okay, a mole of any substance, really, is a very, very small amount of substance. If I had to have a mole of sucrose, which is the sugar that you eat, okay, or hopefully do not eat, all right, because you have to watch your blood sugar levels, a mole of sulfur, a mole of salt. These are all very, very, very small masses, very small amounts of substances, because as we said, atoms are so tiny and therefore so light. Let's now move on to our next slide. There is a very important equation that you should take time to learn, but I'm not going to ask you to remember this off by heart. I'm going to ask you to reason it out. I'm referring to the equation that you have at the top of the page. I shall mark it. Okay, so I'm referring to this. where we're saying that the number of moles of any substance is equal to the mass of the substance all over the molar mass. Okay? Now this might seem, what on earth is he saying? Well, this is really expressed in the first calculation. Let's reason this out step by step and then we'll test it. Let's look at the first calculation. Calculate the number of moles of carbon dioxide molecules in 22 grams of carbon dioxide. It's the first calculation in chemistry using moles and converting those moles into a mass, okay, of the substance. So the first thing that you have to do is notice what the examiner wants. The number of moles of carbon dioxide. In other words, we have to convert the mass of carbon dioxide into moles, into the number of molecules of carbon dioxide. In other words, we're converting mass into a number, a quantitative number. Now, remember that the relative atomic mass of carbon is 12 and the relative atomic mass of oxygen is 16. So we can say what the relative molecular mass of carbon dioxide is, and as we've already done, since we have one carbon, it's 12, and two oxygens is 16 by 2, the relative formula mass of carbon is 44. But we said, if we had to express the relative formula mass in terms of grams, okay, what do I get? 44 grams is the mass of 1 mole of CO2. So if I know that 1 mole of CO2 weighs 44 grams, well, by direct proportion, isn't it? If I have 22 grams of CO2, I must have half a mole or 0.5 of a mole of CO2. And since 1 mole is equal to 6.02 times 10 to the 23 molecules of CO2 in this case, so that is 1 mole of CO2. If I have half a mole of CO2, as I have in this case, because I have 22 grams, not 44, therefore, half a mole is 6.02 times 10 to the 23 molecules of CO2 division by 2, which works out to be exactly 3.01 times 10 to the 23 molecules of carbon dioxide. Now look at the equation that you have at the top. The number of moles, okay, so the number of moles, which is what I want to calculate, is equal to the mass. The mass was given to us. It was given as 22 grams, okay, all over the mass of 1 mole. The mass of 1 mole of carbon dioxide is 44. So the number of moles I have is 22 on 44, and that works out to be exactly 0.5, okay? So you can also use the equation, but do reason it out in the way that I did it over here. Now the best thing to do is to replay the slide, replay it very slowly. That is why I've marked up every part of the calculation in order for you to better understand it. In extremis, if you don't understand it at this stage, there are other calculations I'm including to help you along the way. Okay? Let's now get on to the next slide. So this is a further extension of the first example. So you are being asked at this time to calculate the mass of 2 moles of carbon dioxide. Whenever you're given something like this, start off with the RAMs. Okay? So I'll put in the calculation all at the top. Look. So CO2 is this. Now in CO2, we have 1 atom of carbon, which has an RAM of 12, and I've got 2 atoms of oxygen, which therefore have an RAM of 16 for one oxygen atom and 16 for the next oxygen atom. All in all, we say that we have a relative molecular mass equal to the sum of all of the RAMs. So that works out to be 44. Now, if I had to express that RMM, so remember, so far it's an RMM because there is no unit. But if I had to express that in grams, so I put it down as 44g, that is equal to the mass of 1 mole of carbon dioxide. The mass of 1 mole, or the molar mass, the mass of 1 mole of carbon dioxide. Okay, so the mass of 1 mole of CO2 weighs 44 grams. But we are being asked to calculate the mass of 2 moles. Since 44 grams is the mass of 1 mole, therefore, logically, 2 moles of carbon dioxide will weigh twice as much, 88 grams. Also, for our own interest, 2 moles of carbon dioxide will have this many molecules. Where do I get that number? All I have to know is this. Look, 1 mole of the gas contains 6.02 multiplied by 10 to the 23. And if I have 2 moles, all I have to do is to multiply the first bit. Don't worry about the second bit. Just multiply that by 2. And you know the number of molecules in the gas. So if I know that 1 mole of CO2 contains 6.02 times 10 to the 23 molecules, therefore 2 molecules will contain 12.04 because it's 6.02 multiplied by 2. 12.04 times 10 to the 23 molecules of this gas. Let's now move on. Okay, just one final example to make sure that you've understood what I really wanted to convey today. Let's imagine that we have to find, okay, if we have, for example, the problem as it is written, 10 moles of carbon dioxide, okay, 10 moles of carbon dioxide have a mass of 440 grams. So now we are being asked everything in reverse. Okay, we are given that 10 moles of CO2 have a mass of 440 grams. So we are being asked what is the relative molecular mass of carbon dioxide based on that information. So all you have to do is this, look. Since 10 moles of carbon dioxide have a mass of 440 grams. So I would suggest that you write the information as given at the top. This is what I used to do when I was your age. Look, 10 moles, okay, is equal to 440 grams, right? Now, it's very simple really. So therefore, by definition, 1 mole weighs 44 grams, isn't it? But hadn't we said that the RMM is equal to the mass of 1 mole without the grams? Okay, if you remember, we said that the RMM is converted into 1 mole of a substance, into how much a mole of a substance weighs by adding a G. So 1 mole of carbon dioxide weighs 44 grams. If I had to remove the G, I'm back at the RMM of CO2. That is all you have to do in this calculation. And the RMM of CO2 is the result of having 1 atom of carbon, which has an RAM of 12, and 2 atoms of oxygen, which each have an RAM of 16, meaning that if you add up the RAMs of all 3 atoms, they give you 44 as the final RMM. Okay, also note what I've done at the bottom over here to help you out also with really understanding all about moles. Since 1 mole of CO2 is 6.02 times 10 to the 23 molecules of the gas, if I have 10 moles of CO2, then I would have 6.02 times 10 to the 24. Notice that the increase in the digit from 23 to 24 would represent a 10-fold increase in the number of moles. Okay, that's it. That's the second lesson. Okay, so at this stage you should have gained some confidence with RAM, using RAM to calculate RMM, RFM, you also have gained your first experience with using the idea of the mole in calculations in chemistry. Thank you for having watched this lesson. Okay, there will be further lessons in order to cover the entire material of Learning Outcome 10. That's it, and thank you.